All right.
Wow, this is a big audience. I'm impressed. I've spoken a few times at the Googleplex in Mountain View, which is actually very close to where we are headquartered, our foundation. I'm also speaking at Google in Boston in a couple of weeks, so I seem to be doing a lot of this right now. But I had no idea that Google even had a campus in Tel Aviv, let alone that it was quite so big, and I'm delighted that so many of you have been able to take time to come and hear a little bit more about the work that we're doing and how it's so important. I've got to be one of the luckiest guys in the whole world. You know, I work on exactly what I want to work on, and I was able within only a few years to rise to being essentially, the pinnacle of my chosen field of endeavor. I actually did pretty much the same thing 10 years previously in my previous career when I worked in artificial intelligence research and more or less rewrote the textbooks on software verification. So life is pretty good for me, and I can drink beer while I'm working, which is not so let me try and get going and explain this phrase here, rejuvenation biotechnology. I mean rejuvenation in the strict sense here. I mean actually not just slowing down the aging clock, so to speak, but really turning it backwards, developing therapies which will be able to make your biological age, your physical and mental function more useful than it was before the therapy was administered. That's what SENS Research Foundation works on. It's built on the ideas that I've been putting forward since around the year 2000, and we're making some progress. As you've heard, we're not just talking about it, we're really doing it. You all know that the aging population is growing across the whole world. I know that in Israel, where you still have a very high fertility rate relative to most developed countries, that things are a bit different, that the proportion of the population which is over the age of 65 is relatively low, but still this sort of thing is happening qualitatively. These are US statistics from 1950 to projections to 2050, and the proportion of the population over 65 goes up from 8% to 22%. That, of course, is, the celebration. It's absolutely awesome that so few people die at an early age these days, and that this sort of thing can happen. But, at the same time, we know that by solving the problems of infectious diseases killing babies and killing women in childbirth and so on, we have created, or at least made more serious, other problems, the problems of ill health of old age. We know that the progress that we have succeeded in making against the diseases of old age has been relatively tiny as compared to what we've done against most infectious diseases. So, as engineers, as technologists, it's natural for us to ask the question, why? What gives? What's so special about the diseases of old age that makes them so intractable? And in order to answer that question, the first thing to do is to come up with a definition of aging. And again, as technologists, especially as technologists in the IT industry, one thing that you all understand really well is that vague definitions do far more harm than good. Definitions have to be precise, just like protocols, just like anything. So here's the definition that I'm going to use today, and it's not a controversial definition at all, but it's a definition that is much more precise than most people give, and it's mechanistic, and it's actually useful for orienting our thoughts around how we might do something about aging. So aging is a side effect of being alive in the first place. It's the lifelong accumulation of damage to the body as a side effect of the body's normal operation. And that damage, I'm going to define damage as well. Damage is something that eventually, when it accumulates to a sufficient abundance, makes the body work less well, contributes to age-related physical or mental decline. So the body is built really well to tolerate quite a lot of damage, and that's why the diseases of old age do not affect people of the ages up to, let's say, 50. But eventually, when it accumulates too much, things go wrong. So what this means, and this is, I think I want to explain right at the beginning, it's really bizarre that this is so unappreciated. What this means is that the diseases of old age are caused by aging. They are parts of aging. They are aspects of the later stages of this lifelong process of accumulation of damage. So this means, first of all, as I already said, that they're very widespread now that infections are relatively rare. It also means that they're staggeringly costly because these diseases progress rather slowly compared to most infections, and therefore you get sicker and sicker and we spend more and more money trying to keep you alive. But also, they're not like other diseases. First of all, they are universal. You will get Alzheimer's disease if you don't die of something else in time. Right? That is how it is. And so they're not medically curable in the normal sense of the word cure. We cannot invent some kind of therapy that you can apply once to the body that will eliminate a disease like Alzheimer's from the body in the same way that we can eliminate tuberculosis by a vaccine or whatever, by an antibiotic. Rather, it's a side effect of being alive in the first place. That means that curing it would require curing being alive in the first place, which would rather defeat the object. So let's not do that. Let's instead figure out the fact that they are aging is a medical problem, right? And therefore the diseases of aging are medical problems. And they are medically preventable, but we have to think about a different way to do that. This is a simple way of classifying diseases and problems of ill health that really drives that home. Diseases are normally considered to fall into these three categories. There are communicable diseases, infections. There are congenital diseases that a small number of people have because of mutations that they're born with. And there are age-related diseases that everyone gets eventually if they don't die of something else. But they're all considered to be diseases, and most people think about them as potentially addressable by medicine in more or less the same way. And then out here, there's this weird other thing called aging, which is not a disease, and which has these somewhat ill-defined characteristics like frailty, and that's sarcopenia, that means just loss of muscle, or immunosenescence, decline in function of the immune system. And we kind of don't think of those as diseases. Well, that's bullshit. This is how we should be thinking about those things. These are diseases, yes, but these are not. These are just the bits of aging that we have taken the trouble to give names to. That's the only difference between these things over here and these things over here. They are all parts of aging. And once we get that into our heads, a lot of things become a lot clearer and a lot more easy to see how to address. Here's my definition of aging, written down in 3 words. Metabolism, the word that we can use as biologists to denote everything that goes on in the body that keeps us alive from one day to the next, the normal operation of the body. Metabolism does a lot of good things, but it also creates damage, which accumulates over time and eventually causes diseases and disabilities, pathologies. Everything that we do in the clinic today that is addressing the diseases and disabilities of old age is this, geriatric medicine. And geriatric medicine consists of completely ignoring everything that I just told you over the past couple of minutes and treating the diseases of old age as if they were diseases, as if you could attack the actual symptoms and eliminate them, pound away and eliminate them from the body. Once you've even heard a few minutes of me, you've understood, I hope, that that's completely never going to work. Because these disease pathologies are caused by this accumulating thing. So anything that we do of this nature is going to become increasingly less effective as the damage continues to accumulate and the pressure for the disease to progress increases. No chance. It's better than nothing, but it's only very slightly better than nothing, and that's how it's always going to be. The only reason that the medical profession is fixated on this is because it's all they've got. You probably know the phrase, if the only tool that you have is a hammer, then everything looks like a nail. This is a fine example of that. Now, a small number of people over the past century or so have understood that this is never going to work, and they have adopted another approach, which I'm going to call the gerontology approach. Gerontology approach basically says, let's adopt the fact that prevention is better than cure, and let's go in here at an earlier stage in the chain of events. Let's try to clean up our metabolism, clean up the way the body works, so that it does everything we want it to do, but it doesn't create damage, or at least it doesn't create damage so quickly as it normally does. If we could do that, marvelous, we would have delayed the age at which damage accumulates sufficiently to cause pathologies. Great. Couple of problems. First problem is that it doesn't work so well if you start late. if you're middle-aged already and you've got a lot of damage carrying around, then the very weird. All right.
Wasn't any.
Just as long as no more of them go off, I'll be all right. You know, if you're already carrying around a lot of damage, then even if we shut off or we halve the rate at which more damage accumulates, that's not going to give you so much. That was someone joking. That was someone joking. I'm sure that was someone trying to be funny. It's not going to make so much benefit as if you have this therapy applied throughout life. So that's a shame. But there's another, even worse problem with the gerontology approach. Just as aging is complicated, these are the pathologies of old age, some of them, and you're not supposed to be able to read this slide, don't worry. I just put it up there to emphasize how many things go wrong with us in old age. Similarly, the way the body works, with no comments, and fix it up so that it does this bad thing more slowly without, at the same time, having unintended side effects that do more harm than good. And of course, that's an understatement of the problem. The real problem is not that this is a small subset of what we know about how the body works. This is the problem. The problem is that this is a simplified diagram of a small subset of what we know about how the body works, which is completely dwarfed. Any biologist will agree with this. Completely dwarfed by the astronomical amount that we don't know about how the body works. Even ignoring all the stuff that we don't even know that we don't know. So, you know, it's a waste of time at the moment. It's not doomed in principle the way that the geriatrics approach is, but it's an idea whose time has definitely not come. So, what do we do? Well, what we do is, as engineers, we have a look at existence proofs, at examples, at hints that we might get from elsewhere. And this is a fine place to start from. The things that we do already successfully to extend the healthy longevity of simple man-made machines ought, in principle, to work, equivalent things ought to work on this really, really complicated machine called the human body. Because ultimately, we're just machines. So, what do? This is what works, preventative maintenance. This car was not designed to last 100 years the way it has. It was probably designed to last only 10 or 20 years. The reason it has lasted is because its owners have fallen in love with it and they have done much more comprehensive maintenance on it than the law required. And lo and behold, it has succeeded in maintaining the performance of this machine just as it was when it rolled off the production line. So in the human body, what that means is this, the maintenance approach. We do not try and slow down this process where metabolism creates damage, and we also don't try to slow down this process where damage creates pathology. Instead, we dive in and separate those two processes from each other by periodically repairing the damage, so that even though it's being created at the natural rate, it doesn't actually elevate to the level of abundance that is bad for us. And the reason that is so promising, relative to the other two approaches, is that it avoids the problems I mentioned. It's sufficiently preventative that it doesn't have this problem of accumulating precursors. This is not some kind of downward spiral that affects the geriatrics approach. But also, we're not interfering with this terribly complicated thing we don't understand, this network of processes called metabolism. We're letting metabolism do its thing, and we're going and targeting the side effects of metabolism that are harmless until they have accumulated to too much abundance. So what does that mean in actual practice? This has all been terribly theoretical and abstract so far. It's time to talk about real biology. What it means is we need, first of all, to say what is the damage. We need to characterize that damage reasonably precisely in order to understand the nature of the problem we're up against. And so back in the year 2000, I put forward the classification you can see here, in a slightly different form, but more or less this form. And it's pretty simple, as you can see, a manageable number of categories. There's 7 major types of change that happen at the cellular or molecular level to the way the body works, and which eventually contribute to age-related pathologies of one sort or another. So in this short talk, I don't have time to go through the details. I wrote a book about it a few years ago, which I'll mention at the end. And you can obviously ask me plenty of questions, and you can go to our website and find out more. So just in very brief summary, the idea here is that we look at everything that happens throughout life. it doesn't actually make much sense if you want to understand the nature of aging to look at old people, because it's too messy by then. Lots and lots of things are going wrong over that time, and they're affecting each other, and it's very hard to tell which things are primary and which things are secondary adaptations and such like. That's much more straightforward and much more useful if you look at the difference between, let's say, a 25-year-old and a 45-year-old. A 45-year-old is generally, as long as they're not terribly overweight or anything, they're generally working pretty much as well as they were 20 years previously. But something must have changed that is responsible for giving them a much shorter remaining longevity. So you actually just ask, what are the differences? And this is more or less what you come up with. Plus also, there is a nice circumstantial argument for why this is an exhaustive list. It's been the same list for about 30 years. All of these things have been major topics of discussion and research in gerontology since at least the early 1980s. Now, granted, no one was really looking for a classification like this until I came along and started to offer this one, but that was quite a long time ago now. It's more than a decade that I've been challenging my colleagues to come up with number 8 and number 9 to add to this list, and I seem to be getting away with it. Nothing seems to be happening. So this is pretty compelling evidence that this really is an exhaustive classification. Now I want to spend a few minutes emphasizing the links between damage and pathology. How much we know about the ways in which these various types of molecular and cellular change throughout life eventually cause the diseases and disabilities that we don't want. Sometimes the relationship is very straightforward, and that's one-to-one relationship. Division-obsessed cells, that means cells which are dividing when they're not supposed to. That's pretty much the definition of cancer. So it's a nice simple thing. But other things are not nearly so simple. The heart is something that kills us quite easily, quite often, and there are lots of different things that go wrong in the heart. Different people die of different types of heart disease. So, for example, atherosclerosis, the accumulation of fatty deposits in the major arteries, is ultimately caused by the inability of certain cells in the artery wall to metabolize stuff inside them, and I'll talk more about that in a few minutes. Arteriosclerosis, the hardening of the arteries, the stiffening of the arteries, which is responsible for high blood pressure and all the things that causes, kidney failure and so on. That's this thing down here, the accumulation of molecular cross-links, chemical bonds, in what's called the extracellular matrix, the lattice of proteins that hold our tissues together. And then there's something called amyloidosis, senile cardiac amyloidosis, which is a relatively new discovery, but even though it's a new discovery, it didn't increase our number of categories because it very clearly comes under this category of extracellular junk, meaning molecular waste products that accumulate in the spaces between cells. It seems to be a very major contributor to death of the extremely old, people over 100. Finally, sometimes people's hearts just stop because the brain is not telling the heart strongly enough that it needs to beat. And that's because the cells that respond to the brain's signals, the cells called pacemaker cells, die, and they are not adequately replaced by the division of other cells, so eventually there are too few of them. That's this top category. So the heart is a complicated thing, but the point is, even though it's a complex relationship, nevertheless, we know a lot about it. We can say with great confidence that these are the types of reasons why the heart stops, and these are the cause and effect relationships between damage and pathology. Here's another example, Alzheimer's. Alzheimer's is defined as a disease characterized by these two things, which are called tangles and plaques, two different types of molecular waste product in the brain, and it's also characterized by the accumulation of loss of cells. In other words, cells dying in the brain and not being automatically replaced. So again, it's a complex relationship, but it's a relationship we know. Frailty, this kind of non-disease, diffuse, poorly defined concept of going downhill, again, it comes down to almost all of these things, arguably not cancer, but everything else. So the question then is, what do we do about it? Do we have a solution? And of course, I wouldn't be going around the world talking so much about this if I didn't have a pretty good idea what to do. Preventative maintenance, the maintenance approach, comes down to four main themes. We talk again with there they are: replace, remove, repair, or reinforce. And they fit into the 7 categories in more or less this way. What that means in practice is this. You've all heard about the first one. You all know what stem cell therapy is. Stem cell therapy is the maintenance approach for dealing with this category of damaged cell loss. It involves putting cells into the body that will divide and differentiate to replace cells that the body is not replacing on its own. And, as you know, it's going pretty well. There are many types of stem cell therapy in clinical trials already. Okay, 5 minutes, fine, in clinical trials that are making good progress, including for the diseases of old age. So, Parkinson's disease is a great example where stem cell therapy is showing enormous promise. Since I've only got 5 minutes, I'm not going to try and go down this list, but I will tell you that almost all of the others are at a much earlier stage of development, and that's why SENS Research Foundation exists. We're a non-profit based in California, and we have to be because the work that we want to do, the work that we know needs to be done, is generally too long-term in terms of commercializability to be of much interest to the private sector yet, though that's of course changing. I'm sure you all know that Google has recently created a company called Calico, which with a bit of luck will be paying attention to some of all of this very soon. However, yeah, that's the case, and also these are really ambitious goals, which is not to the liking of public funding of research. So it's a tricky thing, and philanthropy is a good way to make progress in all of this. In the short term, this is what we need to do. We need to reorganize medical research to understand that the diseases of old age are parts of aging. There is some progress in this, even in the National Institutes of Health in the US, but it's going really slowly, and it may not go anywhere because there's so many vested interests in keeping things the same. Eventually, most medicine, most effective medicine, will be preventative medicine against aging, against the diseases of old age. Today, most medicine doesn't work for the elderly, we know that, but it will. It's going to be completely different. In the long term, it's going to be like this. Things like Alzheimer's and macular degeneration and cancer will be just as rare as tuberculosis is today. That's where we want to be. This is our research advisory board, just to show you that I'm not just one person spouting this stuff that's basically science fiction. All of these scientists here are world leader luminaries in their various fields, all the fields that we're working on. These are people that have really gained credibility and that you don't argue with when they endorse something, which they all have, of course. This is Bill Hazeltine, the guy who invented regenerative medicine. This is Maria Blasco, who runs the Spanish equivalent of the NIH. Let's see, this is Nadia Rosenthal, who runs the biggest regenerative medicine institute in the Southern Hemisphere. This is Mike West, who founded Geron and also advanced cell technology and is doing even more exciting things now. But these are really top people. So I'm just going to whip through a little bit for a couple of minutes about the sort of things we do. As I say, we need to be working on all of these things, especially the ones with 2 exclamation marks, because nobody else is. And this one here, the elimination of waste products inside the cell, is something that's really responsible for cardiovascular disease and also for macular degeneration. We're working on both of them. This is the beginning of cardiovascular disease, white blood cells turning into what are called foam cells because they've been poisoned by chemicals called oxysterols, oxidized versions of cholesterol. This is the most important one, 7-ketocholesterol. And the way we're tackling it is head on. We're not trying to take an indirect approach like statins that mess up your cholesterol metabolism in general. We're saying let's find bacteria that can break down 7-ketocholesterol, which we can't naturally do. Let's find out how they do it, the genes that they use. This is a mass spectrometry experiment that we use to do that. Then let's modify those genes to go to the right place in a human cell. This is just showing that we were able to do that. This is the lysosome, this is our protein, this is an overlap. And then let's see if it works. Let's make it work. And this shows that it does. The right-hand side, each of these groups is a different concentration of 7-ketocholesterol, and the right-hand bar is taller in each case, showing that we are bacteria first. That was like 6 years ago, so this is really hard stuff, but we're getting there. The longevity side benefit will be, okay, yeah, 1 minute, perfect. The longevity side benefit will be huge, probably. We are expecting not only that we will get maybe 30 or so years of additional longevity given to people who are already in middle age when they start the therapies, we'll get maybe that much extra life from these therapies, which I think we have a good chance of developing in the next 20 or 30 years. But also there's this concept that those of my work may have heard of, longevity escape velocity, which basically says that the time we buy in those 30 years to improve the therapies will almost certainly be enough to keep one step ahead of the problem thereafter. So we're probably going to look at 4-digit lifespans, but we might not. The question, of course, on all of your minds, therefore, is how soon are these therapies going to come along, the first generation therapies? I think it's 20 to 25 years, but only if we get a bunch of extra funding pretty soon. I think we're probably only going about 1/3 as fast now as we could be if we had proper funding. So that's pretty bad news. We could lose a lot of lives if we don't speed up. You know, people ask me all about the problems that we might create, like overpopulation and dictators living forever and so on. As far as I'm concerned, if anyone who's got 2 neurons to rub together should be able to see that these problems are easy to solve. Certainly that they don't remotely weigh up to the problem that we have today already, the amount of suffering that is caused by the ill health of old age. So I'm not really even interested in talking about them. These are the things that we should be thinking about, the fact that we will not have any age-related ill health. The elderly will be able to contribute wealth to society rather than just consuming it. They'll have the vibrancy and the vigor and the energy to be able to explore new things so that there's no chance of getting bored because they've got plenty more to do. They won't have to retire. They can retire for 20 years and then retrain and become a rock star for the next 40 years. And they won't be a burden on their kids anymore. So this is the book I mentioned that you can go and get. It's very detailed, but it's written for a non-specialist audience, so you certainly won't be reading it in one sitting, but it's all the details you may want to know, and I'll stop there. Thank you very much.